many people know, time is a rigid parameter and cannot be changed. Right? No, according to the theory of special relativity. This is false. Imagine you are at the Formula 1 World Championship. From your POV, this car that just passed you is going at 150 kilometers per hour, but to another car going at 170 kilometers per hour, that same car is going at 20 kilometers per hour. To understand, we need to go to the 17th century and meet with Galileo, who proposed the universal principle of relativity. Galileo stated that nothing is ever stationary. But that doesn't make sense. Aren't I at rest when I am sitting down with my back slouched right now? Well, it's because the Earth is always rotating at 1,700 kilometers per hour on its axis, invariably rotating around the Sun at 30 kilometers per second, without exception traveling through the solar system at 20 kilometers per second, always traveling through the universe at 230 kilometers per second. This is what two scientists Michelson-Morley experiment set out to prove. The Michelson-Morley experiment set out to prove that something called the ether, a powerful fluid that fills the entirety of space, affects the velocity of everything, from which one can calculate absolute motion. The test involved trying to slow light. It was expected that if the experiment was done in different directions, at different times of day and year, results would change, but nothing did. The idea of the ether was abandoned. The speed of light was consequently proven to be constant. This affirmed Einstein's two postulates of general relativity. Light moves at the same speed regardless of the frame of reference, and absolute motion is undetectable. These two postulates created very bizarre occurrences: time dilation and length contraction.
So I'm going to explain the relation between relativistic time and proper time. So at the start, we're going to take the rocket to the inertial frame of reference. And this rocket is, what I mean by an inertial frame of reference, the rocket is traveling at 0 meters a second. And then we have this observer, and he's traveling at 299 kilometers a second. And 299,000 kilometers a second. And then this person inside the rocket, let's say he's Elon Musk, he decides to take out his flashlight right here, and he shines a light going up, and then it goes down. And we're going to call this distance d. And the velocity is c, because we're talking about light here. And so then we're going to use this formula. No, it's a distance formula, and it's d is equal to speed times time. And, or the distance, because the light is going up and down, the distance is equal to 2d. Then the speed, well, because we're talking about light, is c, and c is around, it's close to 300,000 kilometers a second. And then time is just, yeah, it's a relative time, so it's just t stays t. And so then we have this formula, 2d is equal to c times t. Then we want just t by itself, so we're going to divide both sides by c. So then we get 2d over c is equal to the relativistic time. Yep. So now, and this is from the rocket being the inertial point of reference. Now, then we're going to take the observer to be the inertial point of reference, and we're going to see that the distance it travels is going to be completely different from the distance traveled if the rocket was the inertial point of reference. So this rocket now is going at 299,000 kilometers a second, and the observer is going at 0 meters a second, or at rest relative to the Earth. And what we're going to find is that the observer notices that the light, instead of bouncing up and down, actually travels at a 45-degree angle. And it makes and then when light comes back to the ground, the rocket will have traveled at least, I don't know, let's say, yeah, okay, so I'm going to and then light will have gone from will have changed from its initial point where it was shot at, and will be like, let's say it's going to be 10 meters away, and this will be CT, or speed of light times time, half. So I'm going to draw a new triangle, and it's going to be half CT, because the light hasn't traveled completely, the whole distance is CT, and then half VT. This distance here is going to be D, like the one in the rocket of Elon Musk. And then we can use Pythagoras here to calculate the distance. So it's going to be half CT squared from AC squared is equal to A squared plus B squared. So is equal to D squared plus half VT squared. Now, from this we can subtract from both sides half VT squared, and then we get D squared is equal to half CT squared. So now, with this equation, we have to expand the square to the whole expression, and then we get 1 over 2 squared times c squared times t squared minus 1 over 2 squared times v squared times t squared is equal to d squared. Now, we can, from both of these, we can take out a t squared and a 1 over 2 squared. So t squared over 2 squared times c squared minus v squared is equal to d squared. Now, what we're going to do is we're going to divide, because we want t by itself, so we're going to times both sides by 2 squared. So t squared is equal to 2 squared d squared over, and we're going to divide both sides by c squared minus v squared, and this will go on the bottom, this will go on the top. So then we get this. And now we have to square root both sides so that we have t by itself. And so, yeah, 2 squared times d squared over c squared minus v squared, square root of, because since they're both squared, we get 2d. And then here, this is a bit harder to factor out anything, or just square root it. So then what we're going to do is just take a c squared out of it. So we have 1 minus v squared over c squared. Now, square root of c squared is just c, so we have square root of 1 minus v squared c squared. And as we can see, we're going to refer back to this equation right up here, which is relativistic time, and we're going to try to compare it to this one, and we will notice that this the proper time has been multiplied by 1 over 1 minus v squared over c squared, and this is known as the Lorentz factor, and it's represented by a y-shaped looking symbol, and this is how you derive the Lorentz factor. I'm also now going to derive the length contraction formula using what we've derived so far. So I'm going to go back to this part here. So we have half ct squared minus 1/2 vt squared is equal to d squared. Now we want to, from the formula back here, we got the formula for proper distance, which was relativistic distance, to be 2d is equal to ct. And we want this in the same format as this. It's not going to be exactly the same because this is relative and this is the proper one, the one that's viewed from the person at rest. So then I'm going to expand this, and we're going to get I'm going to take out that 1/2 as before. We're going to take out the t squared as well. And then we're going to end up with c squared minus v squared is equal to d squared. And next, since we want this by itself, we want so we have we're going to try to square root it. When we square root it, we're going to we're going to get t times square root of c squared minus v squared over 2 is equal to d. Then we're going to get t is equal to, t times square root of c squared minus v squared is equal to 2d. Now we can observe here that these equations are almost similar, so we now need to take out a c to make it similar to that one. And so, c squared, 1 minus v squared over is equal to 2d. Tc is equal to times the square root of 1 minus v squared over c squared is equal to 2d. Then now we notice that these two, they've both got this Tc and Ct, they're exactly the same. They've also got the same 2d. So that means, and then this length is just multiplied by this, and so this is goes to show that the proper length is multiplied by 1 minus v squared over c squared is equal to the relative length. And so, yeah, we've also derived the formula for length contraction.
After that derivation, hopefully you understand better why time slows down and length contracts as you approach the speed of light. The importance of the Lorentz factor is that it allows us to relate experiences of different observers. So how does this affect your daily life? Well, special relativity affects you when you use the GPS, Global Positioning System, signal on your smartphone. This is because satellites are programmed with correction factors taking relativistic effects into account. The takeaway from this video is that absolute motion is impossible to calculate and that the speed of light is constant at 300,000 kilometers per second.